Have you ever seen two things happen at same time and immediately you thought one must be causing other? It is natural human tendency. Our brains are wired to look for patterns, to connect dots. But in world of data and in life itself, this instinct can lead us down misleading path because sometimes those dots are connected but not in a way you think. Welcome back to Shital's Data Desk. Today we are exploring correlation versus causation, unmasking real story behind data. In this video, we are going to deep dive into one of the most fundamental yet commonly misunderstood concept in statistics, science, and everyday decision making. By the end of this video, you will be equipped with tools to critically evaluate claims, understand research, and even avoid some common logical pitfalls. Let's start with absolute basics. What exactly are correlation and causation? And why is it so crucial to distinguish between them? Correlation simply means that two or more variables tend to move together. When one changes, other tend to change in predictable way. Think of it like dance. Partners move together, but one is not necessarily making other move. Causation on the other hand is much stronger claim. It means that change in one variable directly leads to change in another variable. It is difference between saying they often appear together and A makes B happen. Let's unpack correlation bit more. We often talk about three types of correlation. First, positive correlation. As one variable increases, other also increases. For example, more you study, higher your test score tend to be. Second, negative correlation. As one variable increases, other decreases. For instance, more hours you spend exercising, lower your body fat percentage might become. Third, no correlation. There is no consistent relationship between variables. Color of your car likely has no correlation with your intelligence. Correlation is measured by coefficient, often denoted by letter R, ranging from -1 to +1. +1 is perfect positive correlation. -1 is perfect negative correlation. And 0 means no correlation. So, if correlation is not causation, why do we so often confuse them? It is partly due to our brain's pattern seeking nature, but also because many correlations do imply causation. Sun rising causes day to begin. Eating too much sugar can cause health problems. Problem arises when we jump to conclusions without sufficient evidence. Internet is rife with examples of spurious correlations. Things that correlate perfectly by sheer chance, but have absolutely no causal link. Take classic example. Ice cream sales and shark attacks both increases in summer months. Is eating ice cream causes shark attack or are sharks attack making people crave ice cream? Obviously not. Real driver is hidden variable, warm weather. This is known as confounding variable, but it is just one type of relationship. Correlations can occur for several different reasons. So, let's break them down into four main scenarios. Scenario 1: A causes B, direct causation. This is cleanest and strongest relationship. A directly leads to B. For example, years of scientific research have confirmed that smoking causes lung cancer. Here, we have direct, consistent, and biological supported causal link. Scenario 2: B causes A, reverse causation. Sometimes we observe correlation and jump to conclusions in wrong direction. Take this one. People in hospitals tend to be sick. It's not that hospitals cause sickness. It is that sickness causes hospitalization. This type of mistakes is extremely common in business and social science. Scenario 3: C causes both A and B, confounding variables. This is one of the biggest sources of misleading correlations. Hidden third factor. Ice cream sales and drowning incidents both rise in summer, but neither causes the other. Real cause is confounder hot weather. Confounders act like invisible puppet masters behind the scene. Scenario 4: No causal link, coincidence or spurious correlation. And sometimes two variables move together purely by coincidence. These are called spurious correlations and they can be surprisingly strong, yet completely meaningless. For example, number of films Nicolas Cage appears in correlates with number of people who drown in swimming pools. Or mozzarella cheese consumption correlates with engineering doctorates awarded. These hilarious examples remind us how dangerously misleading raw correlations can be. Now that we have seen all four possibilities, one of them, third scenario, confounding variables, is so important that it deserves its own chapter. Let's dive deeper into how hidden variables shape relationship we observe. Ice cream and shark attack scenario is perfect illustration of confounding variable, also known as lurking variable or common cause. In this case, warm weather is confounding variable. Warm weather causes more people to buy ice cream, and warm weather also causes more people to swim in the ocean, increasing their exposure to sharks. Correlation between ice cream sales and shark attack is real, but it is not causal. It is because of warm weather. Confounding variables are everywhere, and they are primary reason why correlation is not causation. Failing to identify them can lead to dangerously incorrect conclusions. Think about studies that claim people who do X live longer. Often, X might be correlated with other healthy behaviors, socio-economic status, access to health care, or even genetic predispositions. Without carefully controlling for these confounding variables, causal link remains unproven. It is like trying to figure out why car is going faster. Is it new tires or heavier foot on accelerator or the fact it is going downhill? If you only look at new tires and speed, you might miss other crucial factors. But sometimes confounding variables don't just hide truth, they can completely flip it upside down. This is mind-bending phenomenon called Simpson's paradox. Imagine university looks at its admission data. Overall, it seems that men are admitted at much higher rate than women. You might immediately think gender bias causes rejection. But wait, when you break down data by department, you find that women were actually admitted at higher rate than men in almost every single department. How is that possible? Confounding variable here is competitiveness of department. Women were applying to hardest departments with lowest acceptance rate. Men were applying to easiest departments with high acceptance rate. If you look at aggregate data, you see bias. If you look at stratified data, bias disappears or reverse. This is why we must always look deeper than surface level numbers. Another common pitfall is reverse causation. This is when we correctly identify relationship between two variables, but we assume causality flows in the wrong direction. For example, imagine study finds that people who are hospitalized are sicker. This sounds obvious, right? But if you conclude that being hospitalized causes people to be sick, you have got it backwards. It is actually being sick that causes people to be hospitalized. Similarly, if you find correlation between happiness and having many friends, does having many friends cause happiness or does being happy cause people to attract more friends? It is likely a complex interplay, but it is crucial to consider direction of influence. So, if simply observing correlation is not enough, how do scientists and analysts establish causation? They use gold standard built on one powerful idea, control. First and most rigorous method is called randomized control trial or RCT. You take group and randomly split them into two. Treatment group that gets intervention and control group that gets placebo or nothing. Because participants are randomly assigned, only significant difference between two groups is intervention. If there is change in outcome, intervention caused it. This is bedrock of new drug approval and scientific discovery. In tech world, this is called A/B testing. Companies show 50% of their users blue button A and 50% red button B. If red button causes more clicks, they know color caused increase. This is same principle of control and randomization applied to web page. But what happens when we can't control variables or when variables are too big like new government policies? We turn to other strong methods. Method 2, natural experiments. Sometimes life itself creates experiment for us. This is called natural experiment. For example, sudden change in tax laws in one state but not its neighboring state allows researchers to analyze before and after data by comparing state that changed, that is treatment, to the state that didn't, that is control. We can isolate causal effect of new law capitalizing on real world event. Method 3, causal checklist. Finally, for issues like studying long term effects of smoking or pollution, we act like detectives and use causal checklist. Set of logical and scientific tests to build overwhelming case. When evaluating correlation for potential cause, researchers look for multiple lines of evidence. First, temporal precedence. Did cause happen before effect? Second, dose response. Does more of cause lead to more of effect? Third, consistency. Have different researchers in different places found same link? Fourth, plausibility. Is there credible scientific mechanism that explains how cause could produce effect? If correlation checks all these boxes, evidence is compelling and we can be confident in making causal claim. So, why should you care about correlation versus causation? It affects your decision making. Don't fall for headlines that scream, new study shows X cures Y if study only found correlation. Always ask, is this causal or just correlated? This ability makes you smarter consumer of information and it empowers you to make informed decision in every aspect of your life. Next time you hear someone say X and Y are related, so X must cause Y, pause and ask yourself, could there be confounding variable? Could causality be reversed? Is there evidence from control experiment or causal checklist? Remember difference between they occur together and one makes other happen. It is subtle but profound distinction that empowers you to see world more clearly. To recap our journey, correlation is simply relationship where variables move together. Causation means one variable directly produces change in another. Confounding variables, including Simpson's paradox, are hidden factors that can create spurious or misleading correlations. Reverse causation is when we misunderstand direction of influence. Randomized controlled trials are gold standard for establishing causation. When RCTs are not possible, we look for natural experiments and causal checklists to build strong case. Your ability to discern between them is not just an academic exercise, it is vital skill for navigating complex information and making informed choices in every aspect of your life. So, go forth, be curious and always question nature of connection you observe. If you found this video helpful, don't forget to like, share and subscribe for more insights into data and critical thinking. And let us know in comments what other topics you would like us to cover. Thanks for watching.